Yeah. So total voted stake is like they are calculating what is the total stake until now that has been voted for this particular decision. And it is adding in this hash map the account ID and the amount that was voted by every person. I think we need to still check this epoch height, and they are calling this check result function, which is so here they are calculating that if the total
Mm-hmm.
is 100, that means
If it is greater than two-third of the total stake.
it should be greater than 2.
Yeah.
Okay. So if total stake is 100, the voted stake should be greater than 66.
Yeah.
Greater than 67. Yeah, okay. Makes sense. So they are checking if that is the case, then result is they are setting the result variable to the timestamp at which
Mm-hmm.
was achieved, when
Mm.
this figure was achieved. If not, I think it will just remain 0. Okay, this is kind of clear, I guess.
Yeah.
So after this ping, okay, so first they are checking if the result is like, you know, complete or
Mm-hmm.
no. And then we come here, we get the vote of the individual, right?
Mm-hmm.
And we check if the voted stake is less than the total voted stake. Oh, sorry, this is not off.
Mm-hmm.
Voted stake is more than total voted stake. Okay, but I don't understand what is this doing. See, if I
I
have
think this is what this is doing is total voted stake is something that we had defined, right? Like say, for example, 100, and say someone is trying to vote, and that vote is more than the total voted stake. As in, like a person can vote with a stake of say 10, right? It cannot be more than 100,
but
something like that.
total stake, right? So here they have a variable called total stake, which is
Mm-hmm.
validated total stake. Uh, yeah, not. So they are saying that voted whatever I am voting should be
Mm-hmm.
less than total voted balance so far.
Mm-hmm.
Acha, as in till now, if the voted, okay, so if there are 10 people, each of them have say 10 near, okay, that they have staked, okay.
Mm-hmm.
Now, if somebody has already two people have staked as 10 and 10, that means total voted stake so far will be 20. So
Mm-hmm.
I cannot stake more than 20. Means I have to vote with less than 20, right?
Yeah.
That is.
Yeah, that is true. Arey, this is because, see, for example, if someone has already staked 20, and if, say, I come in, I say I have a stake of, say, 30,
Hmm.
then by clearly I will make all the voting in favor of me.
Right. Oh,
Like, yeah.
interesting.
So I think for that they are using this.
This.
Yeah, no one can ever, stake more than the total stakes, like already
That's
there.
interesting. That's interesting, actually. Uh, hmm. To think about how this will work, because staking is something that you would do right at the beginning, right? So some people may stake 10, some may stake 20, some may stake 30, but your stake is calculated. Uh, okay. See, account current stake. It is coming from validator stake, right? It is being inserted into this thing that this account has staked this much currently. So, what if there are lesser stakers who have voted earlier and then a high stake person comes and votes? How will this condition hold? I don't know. I think I have to do some research.
Uh, when you go to total voted stake, where it's defined?
See, total voter state, they're saying total voted balance so far.
Yeah, yeah. See, is there anything use of this variable in the ping function?
Total voter stake is balance. In the ping function, yeah, they keep adding all the account current stakes to total voted stake, right? Whoever has voted till now,
Mm-hmm.
adding that to the variable, right?
Mm-hmm.
So, what if few people who have staked lesser, like smaller validators, came and voted, and then there was a big validator, then his stake will automatically be more, right?
And one more thing, and why they are removing that account ID?
That's just like actually they are just removing this here means it's like popping. So they
Yeah.
quotes hash map, they are just popping the topmost value, which was the current value that was inserted.
No, no, they are, see, a remove function, what remove is doing, it is removing that account ID, key and value,
Correct. And returns the value.
and returns the value. Okay.
Correct. Correct.
So why are we like removing that account ID
Because
from
we
the
don't
votes?
anymore. They have already voted, no?
Okay.
In this vote, they once they have voted, we don't need. See, all we need to know is whether total voted stake overall at any point in time is it greater, it is two-third of the total stakes in the ecosystem. That's all we need to know. Whether two-thirds of people have voted or no.
Mm-hmm.
So once somebody has voted and we have already added it to the this one, then we can just remove it. But I don't understand this condition. Why it should be
Hey,
removed
can you please go to the line where it was written that two-third of the total voted stake?
here. See, this is also coming from environment variable validated total stake. That means how many total number of validators are there and how much each of them have staked put together, I guess.
Mm-hmm.
Yeah. Uh, I think would also be good to see near validators. Hmm. You can see the validators. But I think I still feel like everybody would have staked like different amounts. Okay, let's just roll through this. Okay, I think this is if account stake is greater. No, this is what is a self dot total voted stake. Okay, let's see. In the vote function, voted stake is this. We are getting the top value. If voted stake is less than, okay, self dot total voted stake is total voted stake plus account stake minus voted stake. Okay, and if account stake is greater than zero, then it is inserting.
I guess we can continue the video. Maybe they will say something or explain something.
That's true. That would be better.
If we already reached two-thirds of the validator, then it's just a timestamp at which phase two started. And this is timestamp in nanoseconds because this is how we expose timestamp to within a context. Option means it either exists or doesn't exist. So if it exists, then it's given timestamp. So it means voting already happened and we reach the phase two at a given timestamp in nanoseconds. If it's none, so it doesn't exist, it means the voting was not reached. So we check that if we already reached a vote, if you reach phase 2, then we don't need to do anything. Your vote doesn't matter because it's already phase 2 and the timestamp already there. Then
And for like Rust folks who are, or people who are not familiar with Rust, this whole option some is some none thing is not like a near SDK RS thing. That's just like a straight up Rust thing, right?
Yes. So it's similar how JavaScript has 3 types of Boolean, or maybe more, but it can be true, false, and null. So null is the variable doesn't exist. So similar.
A lot of
here.
languages have null, but
Yeah.
it's worth saying that Rust does not have null. Instead, it has option types, which can return some value or none. And you have to explicitly deal with it where it yells at you. So, but when it gets encoded for the outside world, it is getting like converted to JSON, for example. It is getting stored, sent as null. I think that's what it is.
Mm-hmm. Cool. So next is the query the context of Near SDK, and we check who called us. So there's 3 types of accounts that are available from context. One of them is predecessor. This is the account ID of immediate predecessor of who called vote. So Near is a synchronous environment, and you can have a chain of cross-contract calls. So let's say Alice calls Bob contract, Bob's called Charles contract, and in this case, predecessor is going to be Bob. If we are Charles, then predecessor will be immediate account who called us. In this case, in this example, it was Bob. In contrast, there also signer account ID. This is the account who signed the original transaction. In my example, let's say it was Alice who called contract Bob, and then Bob called Charles. So signer account ID will be Alice, and current account ID is the account of the contract. So in this case, it's going to be Charles, the account of that holds the contract. So on Near, the contract always belongs to some account on which it stores state and has balance and has code deployed. For security reasons, it's very important to always rely not on the signer of the transaction, but on the immediate predecessor. Because let's say Bob is a malicious contract, and if you would rely on the signer, that Bob can call some token transfer contract and withdraw a balance from Alice to themselves or their owner instead of acting on Alice's behalf. So if Bob would try to do this, then the token contract will get the predecessor who is Bob. So contract Bob can only spend balance of their own. So it has some limitations, but this guarantees you that if you call in some contract, this contract cannot really spend your cannot really act on your behalf except on itself. Make sense?
Yeah.
Cool. So next thing we do is
Shobit, you have raised your hand.
Yeah. So this part I'm not able to understand what he said just now.
Wait, actually, they have a good documentation on accounts. It is little like different than how others use. Mm. So they have like the predecessor accounts, and they have something called signer account. So predecessor is like the recent account that is calling, and signer account is the one that called earlier. So they have used this for preventing some kind of fraud. Wait, I will just try to see where that is. Oh, it's not in this contract. Where did he move from? Let's go to account ID. Yeah. Oh, regex filter. Okay. So yeah, so basically because they have this concept of like this function call keys, right? That is full access keys and all. So there can be one account which is the parent account. That's what he's mentioning, like signer account. Now it is possible that the signer account calls a contract that is, so the thing in near is each account is connected to a contract. So like in Ethereum, we have a contract address, but in near, each account holds a contract. For example, market.near, right? This will signify a contract. Then there is alice.near. If there is a contract deployed on alice.near, it will be represented as alice.near, like that. So every contract is stored within an account, right? So what may happen is when we are doing cross contract calls, one contract will call another contract. So bob.near may call another contract which is on alice.near, which may finally call this other contract. So that's why they have this concept of signer account, which is the one that initiated first. And then there is a predecessor account, which recently called. And then I think there is also the concept of current account, which I'm not too sure. Let's see. So did you get the main thing, like how it is different and why accounts are having like this kind of significance? Like every contract that is deployed, no, it's directly deployed on an account, not on like a separate address. How contract address gets generated in Ethereum, right? It's not like that. In this, it is like you deploy a contract directly on an account. I'm trying to find those different types. Or if there is there a contract that he went to from this one? The predecessor underscore account underscore ID. I will remove this. Yeah. So yeah. Predecessor is the ID of the account that was the previous contract in the chain of cross contract calls. So if this is the first contract, it is equal to the signer account. So you got it. If it is like alice.near, there is some contract, okay, like over here called hello world. It may do a cross contract call to bob.near, which is like hello world 2, right? So this predecessor account ID is actually referring to alice.near account, not bob.near. So if some validator tries to call this function using a cross contract call, using another contract in between to create some fraud, it will not take that account. It will take the ID of the account that was the previous one in the chain of cross contract calls. If you're calling this directly, your direct account ID will be taken. But if you're calling through another contract, still your account will be taken.
Okay. Got it.
You got it. So it's
Yeah.
got to do with the way the contracts are deployed on Near. Every contract is deployed on an account. There's not a separate account that is created for a contract. That's the difference in the way we think about how contract is deployed. See, like the signer account ID is the ID of the account that either signed the original transaction or issued the initial cross contract call. So if there are 3, 4, 5 cross contract calls, this signer account ID will go to the initial one, the first one. And current account ID is the ID of the account that owns the current contract. So where the current contract is deployed. So that's why they have like these different types of account IDs. Shall I play this?
Yeah.
Then it means we want to add this our stake from the caller to set of active validators who voted for phase 2. So otherwise, the value is 0. It means we want to set our stake to 0. So we call a special method on the environment, which is calls a host function on Near protocol runtime to get the active stake from the current epoch of a given account ID. It will return for a given validator how much stake they have. And this will be done immediately. So this is a synchronous call. We verified that your stake is 0 or above 0 to make sure that we don't pollute state these non-active validators. So this way we can limit how many validators can get into our state. So because we only have 100 seats when this contract was used, it means you can limit the number of validators in the state of this contract to 100. So basically, if a cert triggers in terms of stake is 0, then we throw a panic, and everything we did before this, all changes to the state, will be rolled back to the beginning of the function call, only for this contract. So in this case, again, coming to example of Alice, Bob, Charles, only state of Charles going to be reverted, but state of Bob is not, because of asynchronous environment. Next, we check if we already voted before. If we did, then we just remove. So votes is a hash map. Hash map is in-memory map. It means every time it's serialized or deserialized, all values has to be serialized into one piece and then deserialized back.
Why did you? Yeah, I think the hash map is interesting. I was just recently talking about this with Mike, actually, and maybe Josh was on that call too. But in general, we give the advice to people that, like, most of the time you want to avoid hash map and use a collection from near SDK instead.
Yes.
And I'm curious why, what makes this a better case for hash map?
Good point. So hash map, as I said, whenever we call a method on this contract, it will deserialize all fields of the hash map. So all 100 potential accounts will be deserialized at once. But it will do this into a single storage read instead of 100 storage reads. So this is that even so the overall size of this is large because each account can be up to 64 characters and balance is 16 bytes.
Okay.
The overall size of this is not as large. So it's 100 times 80, so it's like 8 kilobytes. But we need it in pink. In pink, we have to iterate on every single vote in order to update the stake of the validator. And if we would have to iterate on every single key from a persistent collection, for example, an ordered map, then we will have to do something in order of 100 reads. And in this case, we actually need to override them, which means we need 100 writes. And 100 reads is much more expensive than one-time bulk read of 100 accounts. Because we know that that structure is limited to 100, we don't need to introduce pagination that you might need to do with a persistent map if you would want to iterate. And this is because the trie was stored in, the storage is kept as a trie, and this makes it expensive to do a lot of reads. So in this case, it was beneficial to have one map that you will be able to iterate. So the guideline here would be, if you need to iterate on every single key, you probably want to have a hash map or a vector.
But it's also that you also know that it's bounded, that there won't be more than 100.
Right. Otherwise,
in this case, that's specifically because there's not going to be more than 100 validators for now.
Yes.
Is that correct?
Correct.
And if near were fully sharded, then like this will need to be modified potentially with a persistent map. What are the
either persistent map, or maybe you can do something like a sharded map. We don't have it right now, not or like bulk map. So it will be a persistent map of like bulk objects, because you still need to iterate on all of them. Maybe you can like split your accounts into 20 buckets, and then every bucket will be a vector, but you will store them separately into a persistent map. So when you need to iterate, you only need to read 20 keys, or you introduce some pagination for pink.
Am I correct in saying, I mean, that was a really good explanation. Thanks. Am I correct in saying?
What is pink? What is the actual pink word? I don't think
Ping,
it's pink.
P-I-N-G, the ping function he's talking about.
Oh god.
That like this is kind of min-maxing in the sense that even if you used a near persistent collection instead of a hash map, it's not like it would be crazy expensive, right? But this is just it's just like better, but like, yeah, I guess that's my question.
Right. So currently our storage is probably one of the most expensive operation that you will usually face by default. And if you do like overwriting of them, then potentially it will be more expensive than a hash map, and that's why we picked the hash map right now. But it's not like dramatically worse. But to be safe, we can pretty much estimate that 100 fits into our current gas limits, and it makes it a good choice for this particular contract. Cool. So I think we have like 10 minutes that we want to spend more on this, and let's try to finish some of this. So what happens here is basically remove the old stake. This is just a safety check, and it's an invariant, as it's saying here, which means it's unlikely to trigger in a real environment. So it verifies that the current stake is less than the total stake. Then we subtract the old stake and introduce a new stake. While I would argue that order of this would be better to be first subtracting the old stake and then introducing a new stake.
Oh, I got why they are removing. So they are saying that if you have already voted, so they are removing that and
Yeah.
then inserting the new one, right? Mm. That's why they are checking to vote. So they are saying, oh, this won't happen in real time at all. But then why have they added this check? I don't understand.
Just for safety reason, this you
Yeah.
mentioned.
And they are subtracting the old stake and adding your new stake to the total voted stake.
Yeah.
Okay. It's easy. Okay. Understandable now.
In order to avoid overflows, even so with our limit on total supply, it's not possible to overflow, but you always want to be careful. And finally, if this was an active vote, if it was not a withdrawal, then we introduce this into the storage. And at the end, we will check the result again.
Okay.
So let's go to check result first. So we verify. So when check result is called, we check that the result is not sum. That's another way of checking it. And it also invariant. And we see what's the total validator stake. This is another method that is returned from context. And let's say it's saying we have 100 million total stake. And then internally, this is active stake. It means all validators who voted on this. And we're saying if active stake is more than 2/3 rounded down of total stake, then we reach the result. And that's pretty much over of this contract. So voting has completed. So this is fairly simple method. And we probably want to go to pink. So pink, this happens if on a boundary of epochs. So after an epoch switches, it means the new set of validators became active. Within the epoch on your protocol, validators do not change. So even if someone kicked out, they will be only inactive on the next epoch. So what we do, we verify that we didn't reach the result. Then we take the current epoch height, it's just an integer that always increasing, and we verify that it doesn't match the previous epoch height. So we started with epoch height 0. but every time a ping is called, it is it can update the epoch. So if epoch has switched, so it can pass 1 epoch or 5 epochs, doesn't matter. What we're gonna do, we're gonna go through all previous active votes who voted for phase 2. We reset the total stake to 0, and this is the last way of taking all the data out of hash map and setting it to default. So basically, we got a copy of the map from internal structure, and now internal structure contains an empty hash map. It's a new thing that it was introduced in like recent Rust.
So that sets them all to false. So that's all the same size of votes, but all of them are set to false.
No, it basically just empty hash map. So it calls hash map default, set it to this variable. So let's go here. It basically calls replace. Replace does swap. But a second argument to the replace is a default of hash map, which is empty map. So it gave us a data from our structure, and now this contract structure contains an empty map. And this is just so we can do in one go, modify the current map or the new map based on the data from the old map. So we basically just need account IDs. We don't need to know what was the previous state. So we check if someone was removed from the map, or like removed from the active validators. So we get their stake. If their stake is positive, we add them to the total stake, and we keep their vote. But if they were kicked out, they have to vote again. I don't think this happened during the phase 1. No one was kicked out really from the validating boards. Maybe someone was. I'm not familiar. Actually, I think, yeah, one validator was kicked out. And basically we update total stake by recomputing what's the new total stake. And then we store all the results back to our contract state. And at the end, we do two things. We check the result. So after an epoch has switched, if validators acquired more stake or the total stake decreased, then the result might happen already. And we remember at which epoch we did this. So next time someone calls ping or vote, we don't need to go through this if epoch hasn't switched. So that's pretty much the voting contract. Basically, every time someone calls a vote, we first update data from the previous validators and write it into internal structure. Most important, we get the total voted stake updated, and then we call check result twice occasionally using the one call. And what's important is, even so we can call ping here from one method, but also we can call ping directly via transaction. So you don't need to revote, you can just call ping. So it's pretty much a contract. And the way Rust works, so there's a bunch of view calls. So one of them just returns a result. Another one of them is returns how much stakes go. And the final is a functional way of returning all the votes. It basically iterates on the map and then wraps it into a specific type of the balance using into. So we're almost out of time, but I want to point out that there's also a unit test in the same code, and this is just a Rust way of doing this. And unit test can validate some logic within a contract by faking context and stuff like this. Okay. Any questions to follow up before we close?
This is great.
All right. So let's go back to the call. Okay.
Yeah, I think that's pretty much it. But maybe there will be unit tests in the other upcoming contracts that they will explain. So let's check what is the next. So episode 2. Yeah. Episode 2 is taking full contract. Okay, so let's do this one in our next call. And maybe we should try to, if possible, we should try to view this earlier and come, which I think is not becoming possible. So it's fine. We'll do it in the class itself. And I mean, during our study group session. And all right, I will post the recording of this session